The sigma unknown case is where sigma is what? Anybody?
I'm gonna guess known.
The sigma unknown case is the case where sigma is unknown, right? So wherever you see sigma equals something, you got to change it to question mark because it is unknown. Okay, now when I type in a question mark here, what's going to happen? If I type in a question mark here, whoops, question mark. All of a sudden we can't compute the standard error, the margin of error, and the confidence interval, right? So what do we do in this case? What do we do? If we don't know sigma, what do we do? Anybody? Let's go down the roll here. I left off at Trevor. Trevor, where you at? Okay, I just trying to get the name to the face. Trevor, if we don't know sigma, if we know sigma, we use Z. If we don't know sigma, we use T, right? So when we use T, how do we estimate the population standard deviation, sigma? How do we estimate the population standard deviation, sigma? If the Greek god of numbers did not reveal to us what the sigma is. What do we do? What do we do? Kyle, little review. By the way, you look like the guy from Parks and Rec. Or the guy from Walter Mitty. Doesn't he? You need a beard. You look like the guy that took over at Life magazine, right? Right? Have you been told that? Okay. Well, now you've been informed. So, Trevor, how do we estimate the population standard deviation?
Well, can't you just plug it into Excel? You just get your population listing.
Well, we don't have all the data. We have a sample of data, and so we can't calculate the population standard deviation, but we can calculate the sample standard deviation,
Yeah.
right? S, right? And did we already calculate it?
Yeah.
Mine is 4.897. Now, on Thursday, when the Greek god of numbers, Bikey, was in here, she said, "Oh, the population standard deviation is 5. How many people have a standard deviation from a sample that's bigger than 5? How many people? Raise your hand. Okay, how many people have a standard deviation less than 5? Okay, so some of us, our sample standard deviations are below 5, and for some of us, our sample standard deviation is above 5. Now, in the real world, are we going to know that the true population standard deviation is 5? Are we going to know that? We're not going to know that, are we? This box right here is the confidence interval for which case? Kyle. Which case is that the confidence interval for? Oh, I thought you were Trevor. Did I say Trevor or Kyle?
Well, I think you called me Trevor last time.
Oh, okay. Sorry, Kyle. Kyle,
Yeah.
this is the confidence interval for what?
That would be the sigma. I don't know.
Why would this be the confidence interval for the sigma unknown case? Do you guys see a sigma here? So if you don't see a sigma there, what do you do instead? The sample standard deviation, right? So it makes sense that we call this the sigma unknown case, and that's the confidence interval for the sigma known case. Why? There's a sigma there. There's no sigma here. Right? Everybody got that? Now, if you recognize that, then these problems are really straightforward, right? So instead of going to the Z table, standard normal, aka Z table, aka Z table. Instead of going to the Z table, which table do you go to? You go to the, what kind of table is it? the t-table. So we have the sample standard deviation. We don't know the true standard error, right? We don't know the true standard error because this week the Greek god of numbers decided not to give us the true population standard deviation. So we can't calculate the true standard error or the true margin of error or the confidence interval. So what do we got to do? We have to get the standard error for the sigma unknown case. So, Taylor, how do you calculate the standard error for the sigma unknown case? Which one's the margin of error in the confidence interval? What's the margin of error? I'm waving the mouse pointer across it. What's the margin of error?
You're saying all of those, or what is that letter? Divided by 2.
Divided by 2. Oh, ignore the alpha divided by 2.
Okay.
That's just a subscript. Okay. I got t times s, which is the sample standard deviation, right? Divided by the square root of the
population
sample
population
size.
sample size.
The population size is capital N. Why? Because the sample that we draw from a population, the size of that sample is going to be smaller than the population size, right?
Okay.
So symbolically, we use little n for the sample size. And we use big N or capital N for the population size. Now, what's an example? When I was living in, I did an internship during my PhD program in Cambridge. And I'd walk around downtown Boston. And when I walked around down Boston, I'd observe random samples of people. And all the men were like less than 6 feet tall. And I felt like a giant. Okay, so I formed the hypothesis that Boston men are short. But then when my brother Rod and I hung out in Edmonds, Washington, at various clubs when I was in the Navy, Rod and I were freaked out because everybody, women and men, seemed to be 6'2" or taller at these clubs. So I formed the hypothesis that people living in Edmonds, Washington are unusually tall. Okay? Now, if I wanted to test those theories, would I ask every male living in Edmonds, Washington, how tall they are? Would I ask every male living in Boston how tall they are? No. I could actually randomly sample the male population in Edmonds. I could randomly sample the Boston population, male population, right? And maybe I draw 30 random samples from both populations. 30 in both cases is little n. Big N, I don't even know how many young men live in Edmonds, Washington. Maybe it's 1 million, I don't know. In Boston, maybe it's 2 million young men live in Boston. I don't know what the capital N is for young men in Boston, or the capital N for the young men that live in Edmonds. But if I draw a sample of 30 men from each population, my sample sizes are both 30, right? And I can use that sample average to make a statement regarding the true average of males in Edmonds and the true average height of males living in Boston, right? And if those samples are random, then my X bars, sample means in both cases, are going to be pretty close to the truth, right? Now, if I draw that sample from a gymnasium, a private for-profit gymnasium with only basketball courts, you think my sample might be a little biased? Who generally plays basketball? Tall people. Now, suppose I decided to sample the men in Boston by going into a horse jockey's locker room. Do you think that's going to bias my sample? Yeah, because horse jockeys generally are small or short, and they're light. So you got to be really careful with how you sample the populations. If it's representative and random, then the sample means are going to be close to truth. Now, what is close to truth? Well, we build a 95% confidence interval, right? We know that x bar is not going to be exactly equal to mu. And only Greek gods know the Greek letters. Mu, population mean. Sigma, population standard deviation. Beta, population slope parameter in the linear regression. Only the Greek gods know those values. None of us are Greek gods. So what do? We randomly sample the population. We randomly sample the population. And then x bar should be pretty close to mu. S is going to be pretty close to sigma. B is going to be pretty close to beta. Right? We can compute x bar, we can compute S, and we can compute B. We cannot compute sigma, mu, or beta. Only the Greek gods know those values, right? Only the Greek gods can observe the entire populations. After all, they live in the heavens, right? And they can observe everything. Okay, so going back to my question, what is this thing called?
I still don't know what you're pointing at.
The T times S divided by square root of N. What is that called?
Margin of error. Margin of error.
Yeah. Now, what is just this part called? Not the margin of error, but blank error.
Standard error.
Standard error.
Yeah.
And standard error is another name for what? The standard deviation of x bar, or the mean, right? So the standard error is P Diddy. Standard deviation of x bar is Sean Puffy Combs, right? Two names for the same thing, right? Everybody got that? Okay, so how do we calculate the estimated standard error? We can't calculate the true standard error, right? But we can calculate an estimate of that standard error, correct? How do you calculate the estimated standard error?
So you take S, which is the standard deviation.
Okay.
You divide it by.
And what is your sample standard deviation?
My sample standard deviation is 5.331.
So yours is a bit above.
Mm-hmm.
If Bikey, the Greek god of numbers, was in here, you would know that yours is above 5, right?
Mm-hmm.
Mine is below 5. Why? Because we have different samples. And every time you sample a population, what do you get? You get different sample means and different sample standard deviations, right? And then what do we divide that by?
You divide it by the square root of n, so 49.
And I don't recommend you text your buddy the 4-letter text SQRT. He might not know what you're talking about. Me, I'd assume that you're wanting to take the square root of something, right? I'd assume that you want to take the square root of something. I'd say, what do you want to take the square root of? I'd ask you what number. I'd do a pound question mark if I was texted SQRT. I'd text back pound question mark. Okay, so in order to calculate the margin of error, yeah.
Can you do that one more time?
Yeah. We take the standard deviation, S, right? Mine's 4.897. What's yours?
5.4.
So yours is above, yours really kind of far above 5, right? Mine's only 4.897. And you divide that by the square root of 49. Why 49? How many do I have in my sample? How many do you have in your sample? 49. Okay, any questions? It's probably good that we're going over this again. I kind of went through it a little quickly last Thursday. And plus I want to keep you guys on the same, I want to keep my Monday, Wednesday class at the same point as my Tuesday, Thursday class in terms of course material. Now, we can't use Z. We can only use Z if we know sigma. We don't know sigma, so we use T. Yo, that's the wrap, right? If we know sigma, we go to the Z table. If we don't know sigma, we use T and we go to the what table? The T table, which could have been called the G table, right? So let's go to the T table. And where's my website at? Where's Google Chrome at? I gotta pin it down here. Okay, so you go to my website. The last lecture video was on the Snarr Institute, so you can get there from clicking on that, right? You guys got that? You can click on here to go to my YouTube channel. And eventually I'm going to have the videos for this class on this website too. But you go to teaching, and I'm going to just go ahead and pull up the Z, T, chi-square, and F distribution tables. Okay? And so how many p-values are in the Z table? Over 600. And where are the Z values at? In the column and row headers, right? The Z values are in the column and row headers. So when you combine the row header with the column header, you get this value, right? And if that Z value is negative 2.902, that area there is equal to 0.0018. Now, why do we use the letter alpha? Or alpha divided by 2. Why do we use the letter alpha? I think it's because alpha starts with what letter? A. And what does area under the distribution start with? A. So alpha means the area under the distribution, right? That corresponds to a Z value. Okay? That kind of reminds me, last night I took my son home and he wanted to get some Nutella. So we went and got some Nutella. And we're driving home. He's in kindergarten. He goes, Dad, I like Nutella because it's got an E-L-L-A, irregular vowel, at the end. I thought it was kind of funny. He doesn't like it because it's chocolate. He likes it because of the irregular vowel, E-L-L-A, at the end of Nutella. Nutella, right? Then he starts singing his irregular vowel song from kindergarten. He knows like 800 phonics, and I think there's slightly more than 800 phonics total. Irregular vowels, what else they call them? Consonant blends and irregular vowels. So,
This is the first time I'm hearing these.
have you ever heard that before?
No.
No, that's Challenger School.
Never in my life.
I had no idea that ELLA was a irregular vowel. I think my son's getting a PhD in kindergarten in phonics, seriously, because I had no idea what irregular vowels were or consonant blends.
It's new to me.
Like SH is a consonant blend, right? I never knew that it had a name. I just knew it as SH.
Oh, yeah.
Yeah.
Oh, I get it.
And then OW is an irregular vowel, right?
What's a regular vowel?
Irregular vowel.
Give me a regular.
A regular vowel is O. A-I-E-O-U.
Okay, and then
And an irregular vowel is like OW or ELLA. I didn't know that. I know it now.
Yeah.
Okay.
Alright.
So this is the T distribution, right? Funny, right? He doesn't like Nutella because it's chocolate. He likes it because of the irregular vowel, E-L-L-A. But this is the T distribution, which could have been called the Guinness distribution or Guinness beer distribution. But it's called the T distribution, right? For student T, the author of the paper that discovered this distribution. Now, what are the degrees of freedom equal to? How do we get the degrees of freedom in Chapter 8? When you're calculating the sample standard deviation, right? The thing inside the root is the variance of the sample. When you take the square root of that, you get the sample standard deviation, right? If we knew mu, if the Greek god of numbers, I don't know, Bikey, told us the mu is 25, then you'd use 25 here. But did the Greek god Bikey tell you that? No. So what do you use as an estimate for the mu? The population mean. What do you use? You use the sample mean, right? So when you're computing the sample variance, you're using one estimated parameter to estimate another parameter. And when you use estimates of stuff, what happens to the error in that thing? It kind of goes up, right? If we divide it by n, the statistic is called biased. Is n or n minus 1 bigger? Which one's bigger, n or n minus 1? N. When you divide by a big number, the standard deviation is too small. It's biased towards 0. So what do? You inflate it a little bit. How do you inflate it a little bit? By dividing by a slightly smaller number. Now when n is huge, like 1,000, Does it really matter whether you're dividing by 1,000 or 999? No. Especially when you take the square root of it, right? But when you have a small sample of, say, 10, there's a big difference between 10 and 9, right? Even when you take the square root. So divided by n minus 1 kind of inflates that back up, because we always want to play it safe in statistics, right? Kind of like when we're calculating the minimum sample size. We always round up the calculation for the sample size, right? We're playing it safe. For the same reason, we're kind of playing it safe. We prefer a slightly larger standard deviation, because sometimes your sample standard deviation is less than the population standard deviation, right? Like in my case. But sometimes, like in the Emily case, your sample standard deviation is bigger than the population standard deviation. So you need to kind of account for that, right? So when we divide by n minus 1 here, those are the degrees of freedom. Okay, so if we have a sample of 49, then what do? We have a sample of 49. What row do we go to? 48, right? Now, what's our alpha level? Our alpha level is 0.05, but we have to divide that by 2. Why do we divide that by 2? Cody? Why do we divide that by 2? Where's Cody? Why do we divide it by 2? Why do we divide the alpha by 2? How many numbers are in a confidence interval? X bar plus or minus, so there's 2 of them, right? And alpha is the area in the tail, or alpha is the area in the tails. We have 2 tails here, right? Okay, so how do we get the T alpha divided by 2? In the sigma known case, the Z value was what? What was the Z value? Nick? 1.96, right? Now, what do we expect the T value to be equal to? Let me know. As n gets closer to n, x bar gets closer to u. S gets what? Closer to sigma. What happens to T distribution? It gets closer to what? I call it the Z distribution, aka standard normal. You guys see it? Right, so going back to my question here, what do you expect this value to be close to? As n gets bigger and bigger and bigger, what happens to x bar? It becomes the population mean. What happens to standard deviation of the sample? What does it become? The sample standard deviation becomes the population standard deviation. What does the T become? The Z. You guys see it? Any questions on that? So as that gets bigger and bigger and bigger, closer and closer to the population size, that becomes the population mean, and T becomes Z. This value gets closer and closer to what? This value, right? Is our sample size pretty big? Is 49 pretty big? How do you know what big is? Is 49 big? 30 big? 15 big? 2 big? 100 big? 1,000 big? How do you know what big is in terms of T distributions and standard normal distributions? How big is big?
Don't they consider T's equal to Z's after 100?
After 100, yep. So a sample size of 102 would have a degrees of freedom equal to what? 101, right? 101 is 101 in the Z table. 101 is not in the Z table, right? So a sample size of 102, you just use the Z table, right? Sample size of 102, 102 minus 1 is 100, or 102 minus 1 is 101. It's not in the Z table or the T table, right? So you use the infinity row. So do these numbers look familiar down here? To anybody? Do they look familiar? 1.96, does that look familiar? What is 1.96? Oh, it corresponds to the tail probability of 0.025. Right? So down here, what are these values? They're the 3-digit decimal versions of that which you find in the Z table, right? Let's go to row 1.6 and column 4 and 5 of the Z table. 1.6, 4 and 5. What do we see right here? Oh! 0.0505 and 0.0495. What's the average of the two? 0.05. So you use a Z value of 1.645, right? In absolute value, right? 1.645. What about this one here? 1.282. Corresponds to an area of a tail probability of 0.1. So you go to row 1.2 and column 08. Whoop, negative 1.2 is better. 1.2 and column 08, and you get what? Is that pretty close to 0.10? Yeah. Right? So to 2 decimals, the Z value is 1.28. To 3 decimals, it is 1.282. Do you guys see how it works? So what are these down here? True or false? Those are Z values. True or false? Raise your hand if you say true. Your grade depends on this one question. If you don't get this question right, you fail the class. And I'm raising my hand, so what does that mean? That you raise your hand, right? I'm just kidding, by the way. These are Z values. True, right? True. Is this a true statement? You guys can have fun in here, man. You guys all look like it's Monday. It's Tuesday. Man, come on. I got some good material going on up here, man. Okay, down here in this bottom row, are these T values for sample sizes bigger than 102 or 102? Is that true? Raise your hand if you think it's true. Don't look at me quizzical, Emily. Just raise your hand, emphatically. These are Z values and T values. But they're only T values for sample sizes of 102 or more. They're Z values always, right? What about this? What about this row? Are these Z's or T's?
T.
T's. Yep.
I'm murdering.
Are those Z's or T's?
T.
T's. Are those Z's or T's?
I'm gonna go with T.
T's. What is happening to the value with an upper tail probability of 0.025? What happens to this value here as the sample size shrinks? What's happening to it? It's getting smaller, but it's not too far off, right? Our sample size was 49, so our degrees of freedom are 48, so our T value is what? Pretty close to 1.96, right? Now again, why does it need to be a little bigger? Why does the T value need to get bigger and bigger and bigger as the sample size gets smaller and smaller and smaller? Has to do with this. How good an estimate of the population variance is a sample standard deviation, or the sample variance, when the sample size is small? If you have a sample of 2, right, the variance can be quite large, right? But as the sample size gets bigger and bigger and bigger, what happens to the quality of the estimate? It gets more and more accurate, right? As we add more and more people to a random sample, right? It gets more accurate. Okay, so what was our T value? 2.011?
What was it?
How do we estimate the margin of error, Ashley? We can't compute the actual margin of error, but we can estimate the margin of error, right? Those 3 things?
So you multiply the T.
You multiply the T times the standard error, but it's an estimated standard error, right? Does everybody have different margin of errors? What was the original margin of error? If the Greek god of numbers was here, what would Bikey tell us? The true margin of error is 1.4. Notice My margin of error is pretty close to 1.4, but it's a little bigger, right? It's a little bigger. How many people have a margin of error, an estimated margin of error bigger than 1.4? Anybody have a margin of error smaller than 1.4? How big is yours?
1.34.
1.34. Not off by much, right? Not by much. But most of us are probably going to have a margin of error that's slightly bigger than the truth. Are we going to ever know the truth?
The z-squared.
We're never going to know the truth, right? We're out of luck. We're never going to know the truth. Okay, we're almost done. We're almost done. David. David here? There you are, David. How do we get the lower limit of the confidence interval? How do we get the lower limit of the confidence interval?
I don't know.
Here's the confidence interval, right?
Yeah.
What did we just compute?
What's that?
What did we just compute? What do we call this?
The margin of error.
Okay, so this is the margin of error, right? Now what do? We do two things. We got the sample mean plus or minus the margin of error. So how do we calculate the lower limit of the confidence interval? Ignore the plus. What is the sample mean?
You just do that.
So the sample mean
26. Yeah.
minus, what do we call this? This right here? These three things? The
Margin of error.
margin of error. So what we're going to do? We're going to take the sample mean, right?
Minus the margin of error.
Minus the margin of error. Now, before I hit enter, I'm going to do this. I'm going to copy and I'm going to paste. But I want to change the minus to what? Plus or minus. Right? Plus or minus. This is the plus, and that's the minus. Everybody got it? Now, let me ask you this question. If the Greek god of numbers came in and said, oh, by the way, the population standard deviation is 5, what do you notice about my confidence interval? My confidence interval is pretty close, right? Pretty close. Am I going to notice that close? No. Right? I'm never going to know these values. But I can compute these values, right? These I can compute. These I can't, unless I become a Greek god. And I really don't see that happening anytime soon, right? So I'm not going to be able to do these two. But I can do these two. And look how close I am, man. Look how close I am to being a Greek god. It's amazing how Greek goddish I am. And how Greek goddish you guys are. You guys are really close to being Greek gods. Right? Now, we're not Greek gods. Why? Because we don't know what mu is. Right? We got a pretty good handle on what sigma is, right? At least I do. I'm off by a 0.01. I don't know how far you guys are off by. Right? I'm just barely off. So what does this confidence interval tell us? Is this a true statement? Derek, here? Yeah. Derek, is this a true statement? The probability. Now, what don't we know in this problem? We don't know two things, right? We don't know the population standard deviation. And we don't know what? Mu. We don't know mu, right? That's the whole point. We want to figure out where mu lives with 95% confidence, right? At best, it looks like it's 28.06. At worst, it looks like it's 25.24, right? Pretty tight interval, right? So is this a true statement, David? The probability that the true mean is in between those two values equals 0.95. True or false? Now everybody wants to think it's true. So it's false. Why? Okay, suppose the Greek god of statistics came down to earth and whispered in your ear, David, that the mean is 28.15. Let me ask you the question again. What is the probability that the true mean, now, mind you, Xerxes, he's a kind god, right? Xerxes knows what mu is. And Xerxes says, I'm a kind god. I will give you mu. And you can have all of your mortal desires. You guys in 300? Right? One of those mortal desires is to know the true mean of the true average Atlanta area meal price. Those are one of the desires of man, right? One of the carnal desires of man. So Xerxes tells you the true mean is 28.15. Let me rephrase the question. What's the probability that the true mean is between these two numbers? Between those two numbers, what's the probability? 0. Now, suppose Xerxes said, I'm sorry. The true mean is really, I'm just playing with you. I'm a fun-loving God that likes to have fun with you. 24.12. What's the probability the true mean is in between those two numbers? Still 0. What if Xerxes comes back and he goes, I like it, yeah. It's really 26. Now it's 1. So that statement, the probability that mu's in between these two numbers equals 0.95 is not the true statement, right? It's either 1 or it's 0. It's either in there or it's not. You don't know. You never know. You guys aren't going to know whether the true mean is in your confidence interval or not. However, if we replicate this experiment 1,000 times, how many of our confidence intervals are going to contain truth? If we replicate this experiment 100 times, how many of the confidence intervals will contain truth? 95 out of 100 of the confidence intervals that we'll compute in this class will contain the population mean, the thing that which we seek, right? 5 of you guys, which may be me, are going to be out of luck. 5 of the confidence intervals won't contain truth. If we build 1,000 confidence intervals, how many do we expect to contain truth? 950. But there'll be 50 of us, me included maybe, who by chance, random chance, have built a confidence interval that does not contain truth. Okay? So that's a little disheartening, isn't it? The probability, the true parameter is in your confidence interval is 0 or 1. You don't know. However, you're confident that you're one of the 95 out of 100 that contains truth. Any questions on that? So that is case 3, the sigma unknown case, right? What's the 100% confidence interval? What are these z-values?
1 and 0.
Infinity and negative infinity. So when you multiply your infinity times your standard error, what's your margin of error? Infinity times the standard error is infinity. Infinity plus your sample mean is infinity. Infinity minus your sample mean is infinity. So can you use 100% confidence intervals to make good decisions? Like if you want to compare meal prices in Salt Lake to Atlanta, and you want to be 100% confident, what would happen? The average meal price in Salt Lake is infinitely large. The average meal price in Salt Lake is negative infinity. The average meal price in Atlanta is infinite many dollars. The lowest meal price in Atlanta is negative infinity. Do you guys want to be 100% confident in statistics? No, it's ridiculous. You can't be 100% confident in statistics. You can be 99% confident, 99.9% confident. When do you want to be most confident? 99.9% confident. When do you want to do that? If you make peanut butter and you're testing for E. coli. When do you want to be least confident? When you're selling Chips Ahoy cookies and you come up with an ad campaign that says we have 16 chips per cookie, then be 80% confident or 90% confident. right? You don't want to be 100% confident ever. In our example, they were 95% confident. That's pretty good, right? Pretty tight interval. Full Salt Lakes was 21.28 and 23.89. Where would the cheaper mills be? Salt Lake. Now, hey, I can use that. I can use a 95% confidence interval. I can't use 100% confidence intervals, right?